Welcome back to the Explainer. Since we've already explored the foundational applications of CSDL across so many different fields, we're just going to skip the gentle introductions today. Seriously, no recaps, absolutely no training wheels. Instead, we're dropping you directly into the deep end of general relativity to see if we can tackle today's topic, taming space-time tensors with CSDL's physical relaxation. We're putting on our science writer hats today because we're going to look at the incredibly rigorous and frankly highly controversial realm of theoretical physics. We want to see if the scientific language of CSDL can actually tame a true scientific monster, the chaotic, fluctuating space-time tensors of a theoretical warp metric.
So can a 1.5 square millimeter, 50 milliwatt analog chip compute the fluctuating tensors of a theoretical warp metric? Let's dive straight into this highly controversial, almost sci-fi realm of warp fields. The fundamental question we're asking is whether our ABN-QSS version 2.0 hardware, literally a tiny chip with a footprint of just 1.5 square millimeters that sips less than 50 milliwatts of power, can handle the kinds of nonlinear field equations where multi-million-dollar standard supercomputers just completely fail. We're basically putting the analog array to the ultimate test.
To understand how this actually works, we kind of have to reframe the problem entirely. Think about it. When standard supercomputers try to simulate highly nonlinear partial differential equations, they try to slice up the monster with brute force numerical calculations. They chew through massive amounts of energy, often measured in megawatts, and they frequently just get mathematically trapped in what we call unstable saddle points. CSDL, on the other hand, doesn't calculate in that traditional sense. It builds a physically constructed cage using analog hardware constraints that absolutely forces the math to naturally settle into its lowest energy state. And it does this through a physical relaxation process that takes, get this, mere microseconds.
Let's move into isomorphism, the mathematical bridge linking abstract topology to analog hardware.
So the absolutely crucial point here is that this is not just a metaphor. We are dealing with a literal isomorphism. That means there is a mathematically strict equivalence between the way our CSDL array physically searches for a ground state and the domain wall solutions you find in high-dimensional field theories. Now, I know that sounds super heavy, but what it essentially means is that the physical relaxation of our analog chip is mathematically identical to solving these highly complex topological problems. It's wild. When the voltage on the chip settles, the field equation is just miraculously soft.
And this beautifully illustrates exactly how CSDL solves problems. Imagine a 2.5D energy landscape where a system naturally relaxes into a stable ground state, repelled by a local strain obstacle. The system isn't executing lines of software code or if-then statements. It's physically sliding down an energy gradient. What's absolutely incredible to me is the universal nature of this CSDL language. The chip behaves the exact same way, whether it's generating a repulsive force to avoid a physical drone crash in real time or resolving a massive fluctuation in a warp field tensor. It just simply relaxes into the valley of lowest energy.
Okay, on to the 4D magic hypercube constraint, mathematically validating the physics.
This brings us to a really foundational layer in the CSDL architecture. We literally take the space-time manifold and map it directly into the vertices of a four-dimensional hypercube built right onto the chip. This ensures that the physical nodes maintain specific conservative states. Under this architecture, the system monitors a metric called the symmetry mismatch degree, or D_G. Now, while those terms are definitely highly specific, the core idea is elegantly simple. In our analog model, this physical mismatch corresponds directly to the theoretical scalar fields of the complex physics we're simulating.
We validate all of this by applying what physicists call the Israel matching conditions. By doing that, we mathematically prove that the surface tension of a theoretical domain wall acts exactly like the constraint residual on our physical CSDL chip. And the whole system is actively driven by our L3 adaptive control layer, which is known as the Divine Comedy Protocol. Yeah, it's a pretty poetic name for an engineering protocol, but it does exactly what it implies. It constantly pushes and pulls the physical voltages, ultimately forcing the chaotic fluctuating tensors to settle perfectly into a topologically protected attractor.
And next up, the 38x efficiency singularity. Let's look at the undeniable data.
So what does a 38 times efficiency singularity actually look like? Well, in our specific topological simulation of the warp metric, the chip achieved a state of Lyapunov stability. This physical stabilization resulted in a massive 38-fold reduction in the positive energy deficit when compared directly to the absolute best brute force digital scans. Think about that, a 38 times improvement in a problem that routinely breaks modern supercomputers.
But honestly, what's really staggering in the simulation data is the precision.
The residual deviation is only 0.04%. That raw mathematical deviation proves that this solution isn't just some accident. It's a physically guaranteed topological attractor. We're literally comparing a brute force supercomputer method that requires megawatts of power and frequently fails in unstable saddle points against an analog physical relaxation method that finds a unique Lyapunov stable ground state using less than 50 milliwatts. The efficiency gap here is just frankly unbelievable.
Finally, let's talk about the physical boundaries of reality and sci-fi to really ground the engineering scope here.
Now, we have to draw a sobering, rigorous line between mathematical validation and physical reality. We are absolutely not claiming to build a physical warp drive today. Science fiction loves to imagine building a macroscopic warp ship space, but rigorous physics tells us that requires impossible Planck-scale energy. That's purely sci-fi. The actual engineering reality is that we're validating the ABN-QSS version 2.0 analog coprocessor as the ultimate tool for academic simulations. We're providing a way to solve incredibly complex, nonlinear, partial differential equations. So just to be perfectly clear, this is a vital tool for advancing high-level physics research, not for launching a starship tomorrow.
But even in pure engineering, there is a profound elegance. When the CSDL system achieves Lyapunov stability, it undergoes what we call graceful degradation. The system's voltage slowly decays, the constraints release, and it just settles without any of those dreaded software crashes or error screens. Our research notes actually mapped this physical process to a really beautiful poetic state. You are that branch stripped of flesh, bearing the tremor, yet deep in the marrow, brewing a clear intoxication without a single drop of wine. It just perfectly captures the pure hardware-level resolution of tension. A perfectly clean decay right into zero error.
Which leaves us with such a thrilling prospect. If a 1.5 square millimeter analog array can accurately map the abstract topology of warp metrics using less power than a tiny LED, what other unsolvable scientific monsters will physical relaxation conquer next? We're actively opening up partnerships to the research community to simulate complex physical models using CSDL. The framework is ready. The isomorphism is mathematically proven. So the only question left for us is, what boundary of science will this analog engine shatter next?